Okay, so ladies and gentlemen, if you would, have your equation sheet out, be on the front side, because we're going to use some of those same equations we used last class. And most of what we're going to do today, guys, we're going to move a little further in chapter 16, but most of the processes that we're doing today are the same processes you did last class. So it's really just going to give you some more practice with this. There were two primary topics that we addressed last class. Okay, one was how to deal with strong acid calculations. The other was how to deal with weak acid calculations. Okay, so hopefully you have your notes from last class and you'll remember, you can look back if you need to. Strong acid calculations are very quick, very fast, very easy. Weak acid problems require a little bit more. They required ice tables. Okay? And most of the time, when we're doing calculations in here, most of the time your word problems are going to ask you to calculate a pH. But not always. There are some other things you could be asked to calculate, and that's what we're going to start with today. You might, instead of being asked to calculate a pH, you might be asked to calculate what's called a percent dissociation. That's a term used with acids. If we're dealing with bases, we would call it a percent ionization. Okay? And before I show you how that is calculated, guys, I want you to understand what that term even means. All right, let's take it from the perspective of an acid. Percent dissociation means what percentage of the acid sample splits apart, dissociates, dissolves, ionizes, however you want to say it. What would that percentage be if we're talking about a strong acid? 100%, you're right. Okay, you wouldn't have to calculate anything. Percent dissociation for strong acids, 100%. Weak acids, that number is going to be much, much less. And this is how it's calculated. All right, and this looks more complex than it really is. Okay, but it's simple. Okay, if you would, guys, look back at one of the ice table problems that we did last class. It doesn't matter which one, just pick one. Do you see that at the end of that ice table, you found a value for X? Do you see that? Okay. Well, what's in the numerator here? Amount dissociated. That is X. X, whatever that number comes out to be, that is the amount of acid that has dissociated. Initial concentration, look in one of those ice tables, look on the I line. I stands for initial. Okay? Initial concentration just means what was the initial concentration of that acid on that I line. Okay, times 100. And that's it. Okay, so you would do an ice table just like you normally would. It's just at the end, instead of solving for a pH, you solve for something else. Okay? Now, don't write this down. Okay? Don't even read it. Just don't even read it. It's like going past a car crash. Don't look at the car crash. Okay. I don't want to even address this until we have some numbers in front of us. So I'll come back to this. Let's look at this first question here. And I'm going to weave in some review from last class here. This problem says, calculate the percent dissociation of 1 molar and 0.1 molar acetic acid, and then we're given the Ka value. Okay, first things first. Acetic acid, strong or weak? Weak. Big clue. Strong acids don't have Ka values. If you see a Ka value, you're dealing with a weak acid. I'm going to write out the reaction that occurs here. But before I do that, let me say something to you guys. Acetic acid is probably the most common weak acid that you are going to see. We're going to be doing a lot of problems, and acetic acid is going to come up a lot. If you find it tedious to write out its formula every single time, you have my permission, and sometimes you'll even see this on the AP exam, to write this. Because acetic acid comes up so often, we can write kind of a shorter version of it. Okay? So I'm going to write acetic acid's formula just like that. It's going to be reacted with water. Now this is review. You guys help me here. Let's predict those products. If predicting products makes you nervous, don't let it make you nervous. Keep it simple. What is our definition of an acid? What do acids do? They give away what? Their hydrogen ion. Okay, if this gives away its hydrogen ion, what's left? Okay, acetate, which I'm going to write like this. And where does that hydrogen go? To the water, and it becomes, what's it called? Hydronium. Very good. Okay. So there's your reaction. Here's what I would like for you to do. Set up your ice table. Let's use, I know we're given 2 molarities. Let's just do this one for the moment. Okay, here is your initial concentration. Set up your ice table, solve for X, and stop there. Okay? Do that. Okay? Did you get that for X? Okay. By the way, this came up on Monday in one of my other classes. Someone said, do we have to graph it to find X? I mean, I have a quadratic program in my calculator. Can I use that? Yes, you can. Did you all know that before the AP exam, there's nobody clearing the memory out of your calculators? I don't know if you knew that. If you find that easier to use like a quadratic equation program to find X, go for it. Just make sure that you're using the right X value, because you're going to end up with 2 different values. Okay? Now, guys, if this were last class, we would use this number to find a pH, but that's not what we're being asked for this time. We're being asked to find the percent dissociation. So percent dissociation, again, is whatever you got for your value for X, the amount dissociated divided by the original molarity times 100. And that gives me, let's see, 0.42. Is that right? Yeah. Okay. Now before we go on, guys, I want you just to have an appreciation for this number. What was the percent, what would the number be? The percentage be for a strong acid again? 100%. Look at how small that percentage is, guys. When we say that there's a big difference between a strong acid and a weak acid, we mean it, okay? This is saying that only 0.42% of these acetic acid molecules have separated. 99.5% 0.58% of them stay together. Okay, that's what it means to be a weak acid. Okay. Now, I'm not going to go back to the original problem, but they also asked us to calculate a percent dissociation if this acetic acid solution wasn't 1 molar, but was 0.1 molar. And I'm not going to make you rewrite all of this. Here's what I want you to do. Pick up your calculators. All I want you to do is change the number 1.00, change that to 0.1. Tell me what you get as a new value for X. Zero, 0, 1, 3. Okay, sounds good. Let's recalculate a percent dissociation. I'm running out of room here. And it's not over 1.00. This time it's over 0.1 molar. Now, would you agree this is still a pretty small percentage? Yeah. Okay. But what I'm going to do now, I want you to look at these calculations we just did, and I'm going to read you that statement on the previous slide that I said, don't read it, don't read it. Okay? So look at these numbers and just listen to what I say here. For a weak acid, percent dissociation increases as the acid becomes more dilute. Let me say that one more time. For a weak acid, which is what we were dealing with here, percent dissociation increases as the acid becomes more dilute, which is exactly what we had. Our first situation, the acid was 1 molar. In the second situation, it was 0.1. That's more dilute. And that might seem kind of backwards to you, but I think of it kind of like if you have a severely obese person and then just a slightly overweight person, and both people lose 20 pounds, which person lost more percentage-wise? The smaller person, okay? That's kind of how I think of it, all right? Maybe that's a poor scenario, but that's sort of my thought process, okay? But what I really just want you to focus on here is that you're not always going to be asked to solve for pH. Sometimes you'll be asked to solve for a percent dissociation. Now, you guys are going to do this one on your own. This one is a little different. Okay, let's read it, and then you're going to do it. It says, what is the Ka? Meaning, I'm not giving it to you. You have to figure it out. Of a weak acid. I'm not telling you what acid it is either. This acid is 8.1% dissociated. Here is its initial molarity. Since we don't know what the acid is, guys, let me just make a recommendation. How about we call it this? Since it's some unknown acid. How do we deal with weak acid problems? What do we do? We do an ice table. What I would do write your reaction, set up your ice table. At the end of that ice table, you're going to see that you are missing some pretty critical information, but there's a way to get it. Try this one. You'll love it. Okay, how'd you do? In my class this morning, somebody asked a great question. You know, I feel like I'm really getting the hang of these ice tables. Do I really have to keep writing all of this out? Well, I mean, when you're sitting in here taking notes, no, I can't force you to write this all out. If this were a test question, absolutely you would need to write this all out. However, it is a good idea, even in here when we're just taking notes and maybe you're doing a homework problem, it's a good idea to write it all out because, and this is why I like this problem so much, your unknown, whatever it is you're supposed to solve for, is not always going to be at the end of the ice table. What if, can you imagine, if you are given all of this information, the one piece of missing information that you don't have is this number right there. Imagine if your unknown is the initial molarity. You know everything else, but you don't know that. Having this ice table situation where you could put a question mark right there and work from there, work everything down, it makes it a lot easier to see how you're going to solve for that unknown. Okay? They can put unknowns anywhere they want. Sometimes they're at the beginning, sometimes they're at the end, sometimes they're in the middle. Okay? So I would keep writing this out, but it's up to you at the end. Okay? All right. We are temporarily leaving the land of acids and entering the land of bases. And if you are thinking, I'm going to have to learn a whole new set of processes, you are incorrect. You're not. Guys, we're going to use a lot of the same verbiage and processes the same way. We can say the words strong and weak in the same sense for bases that we use them for acids. Okay? A strong base still means the same thing. Complete dissociation, 100%. The only difference is, instead of, when dissociation occurs, instead of providing H+ ions to the solution, with a strong base, you'll be supplying lots and lots of hydroxide ions. Okay. Now, do you all remember what your strong bases even are? Okay, Cabasser. Everyone always says Cabasser, and that's true. That's good. You remember 3 of your strong bases: calcium hydroxide, barium hydroxide, and strontium hydroxide. But there's more than 3. Where are the others coming from? You'll notice those are all in group 2. Where are the others? Group 1. Your group 1 hydroxides: lithium hydroxide, sodium hydroxide, potassium hydroxide. Please don't forget those. Okay, so here are your strong bases. Okay. Here is a weak base that we will use a lot. What's its name? Ammonia. Okay. Let's just refresh our memory on what it even means to be a base, ladies and gentlemen. Look at this ammonia from left to right. Can you see that ammonia is accepting a hydrogen ion? Can you see that? When you write a base reaction, we're not going to have H3O plus as a product anymore. Now we're going to have OH minus. And instead of Ka values, now we're going to have Kb values. but everything is going to work in the same way. Okay? So don't get too hung up on this is going to be totally different. No, it isn't. Okay? Your weak bases, it means the same thing as a weak acid. Very little dissociation. Most of your weak bases, ladies and gentlemen, their formulas don't even have OH in the formula. Like ammonia is just NH3. There's no hydroxide. They're still proton acceptors. Okay, here's another weak base example. Now I chose this one for a very specific reason, because this is kind of something unique to weak bases. Many of the weak bases that you are going to come across will be compounds you've never seen before. Like this one. Does anybody know what this is? No. Okay. I would not expect, nor would the AP exam, I don't think, I would not expect you to look at this compound and just immediately say, oh yeah, I know that's one of my weak bases. Okay, this is a compound you're probably not familiar with. Don't stress. You will be told in some way that that is a weak base. Maybe I actually say, the following weak base, comma, I mean, that's pretty clear, right? Maybe I don't ask you to predict products. Maybe I write out this whole reaction for you. What is this guy doing? Can you all see that he is accepting a hydrogen? Can you see that? That's a clue. He's a base. Or maybe when I give you this compound, right after it in parentheses, you're given a KB value. That's another big clue. This is a weak base. Okay. Right? But we're going to look at a problem here. All right? The name of this compound, just for your interest, it's called methylamine. Okay? It's an organic compound. It says, calculate the pH of a solution of 4 molar methylamine. And notice, I give you a KB value. Here is what I would like for you to do. I've given you the reaction. It's a weak base. We deal with weak bases just like we do with weak acids. This is an ice table situation. Here's your initial molarity. Set up your ice table. Solve for X. If you feel like you know what to do, go for it. If you're not quite sure, then you can just stop there and wait for me. Okay. Take this and solve for X, please. Now, this part, up until this part, no big deal. It's almost exactly the same thing that we've been doing.
It is.
Okay, it is the same thing, fine. Here's where this becomes a little bit different, just slightly. Last class, when we got to this step, we could find the pH by just saying negative log of what we found for X, because X was equal to the H plus concentration. And a lot of you asked me, is X always going to be equal to H plus? And I said, no, it's not. What is X in this problem? You got it. And guys, don't memorize that. It's in your ice table. Look, OH minus is equal to X. So if I'm not quite ready to find pH first, what's probably easiest to find next? POH, okay. Negative log of this number, somebody tell me what you get. 1.38. How do you change a POH into a pH? 14 minus, okay. Ladies and gentlemen, what do you think I'm going to ask you? Does it make sense?
Yes.
Yes, this was a problem that gave us a weak base. Is this pH in the basic range? Yeah. Don't worry about where is it in that range. We'll get to that later. But is it in the correct range? Yes, it is. Okay. So, here is your final task for the day. Now, this is not as much as it looks like, because let me just say something, and then I'm going to let you go on your own. Can you tell me, somebody tell me, why was it last class, why were strong acid problems so quick, so fast?
Because they equal the things.
Okay. We didn't need an ice table, right? Do you agree? Because whatever the concentration of my acid was equal to that, and we could jump right to calculating a pH right away. Do you think the same thing holds true for strong bases?
Yes.
Yeah. You don't need an ice table for a strong base question. Do these, please. All right. Check them. I'm going to come back to something with this one because I want to show you something that could come up in a strong base situation. Can I move on to number 2? Okay, check out number 2. All right, here's number 3. You can calculate percent ionization the same way you do percent dissociation. I want to show you a situation that could come up in number 1. All right? Let's say you are given the same pH to start with. The question is asking you to solve for the same thing, the concentration of the base, but the base isn't KOH. This is what the base is. Is that one of our strong bases? Yeah. Okay, so it's not like this situation requires an ice table or anything. However, this is going to have an effect. Okay? Did everybody hear me say that? This number is going to change the question. If this were the base I was going for, now, would this number change? Right here, this line. If I'm given this pH, would this change at all? Okay? Would this change? Would this change? No. My OH minus concentration would still be this number. Okay? Up to here would all be the same. So let's think about what would be different. I would have this molarity of OH minus, but guys, and I saw a number of you didn't really pay attention to this. OH minus concentration is not what the problem asked for. It asked for the molarity of the whole compound. So I don't want OH minus. I would want this. For every one of these, how many hydroxides are in there? 2. The answer to this question would be different than if it was KOH. Okay? You have to be careful with that, guys. 3 of our strong bases, Cabasser, are going to have that little 2 there, and it's going to make a difference. It's It's not going to affect the OH minus concentration, but it would affect the concentration of the whole compound. The reason I didn't have to worry about that in this problem is because if I did this, these numbers would just be 1 and 1. I just wanted you to be aware of that. Make sure you are careful. I'm going to stop there.